We're going to spend the remainder of this unit looking at the three basic configurations for our MOSFET amplifiers. And so we're going to look at this table which sort of summarizes their behavior before looking at the individual configurations for a couple of reasons. One, we're going to see that there is a lot of similarities between these amplifiers and their BJT counterparts, so we kind of already have an idea of what to expect. And the second reason being that at the time of recording this video, we don't exactly have enough time to go through some more details, particularly with our common gate configuration. So I think it's good to sort of get an idea of what's going to be going on with all of them first, because we won't have sufficient time to look at each one of them individually. So with that being said, let me first point out sort of this commonality between our MOSFET configurations and our BJT configurations. So as you might have noted before, of course, we have this very strong correlation, or correlation is not the right word, but a very strong similarity between our MOSFET and our BJT. And so we could say our source is a lot like our emitter for the BJT, our drain is a lot like our collector, and so the two names for these terminals, emitter, collector, source, drain, even kind of have the same idea, sort of the general sense of what the terminal is doing is the same. And then of course our base is similar to our gate. So with that in mind, let's go ahead and fill in this table. And so let me also note that this is adapted from a table 4.2, which is on page 238 of the textbook. So let's start by looking at our common source. So we're going to be in this first column over here. So our common source circuit, it turns out, is going to have a voltage gain greater than 1. And so that's similar to what we saw with our common emitter configuration for our BJT. For our current gain, it turns out that we're not actually going to have a current gain, and we'll talk about why that is a little bit later. The input resistance is going to be R Thevenin, and so as we'll see noted below, that's essentially just the equivalent resistance of our biasing network. Our output resistance, we don't have a specific value, but for this particular configuration, it is going to be moderate to high. And so we have a little footnote with that red cross there, and we'll come back to that a little bit later. For our common source configuration, our input is always going to be defined as at our gate, and our output is defined at our drain. So again, similar to our common emitter amplifier that we saw when we were looking at our BJT circuits. For our common drain, which is also called a source follower amplifier, we see that our voltage gain is approximately equal to 1, but just like we saw with our common collector or our emitter follower, it's going to be slightly less than 1. So it's going to be something like 0.9 or 0.95 or something a little bit less than 1. Again, we're not going to have any current gain, and we'll talk about that when we get a little bit later on. We'll talk about that. Our input resistance is also going to be that Thevenin equivalent of our biasing network, our input network. Our output resistance for this configuration is going to be low, and we'll talk about advantages of that a little bit later on. And our input for this configuration is also defined at our gate, and our output is now defined as at our source. So the final configuration is our common gate. And so in this case, we have a voltage gain that is again greater than 1. And our current gain, in this case, we do have a defined current gain, and it's approximately equal to 1. But like our voltage gain for our common drain, it's going to be a little less than 1. Our input resistance for this configuration is going to be low, and then we're going to have the same moderate to high output resistance that we did for our common source configuration. So moderate to high. For our common gate, our input is defined at our source, and our output is defined at our drain. Okay, so a couple notes about this table now that we have it fully filled in. So first, let's take a look at this footnote indicated by these red crosses. So this moderate to high output resistance, that output resistance turns out is dominated by our drain resistance, R sub D. And so we'll see that more clearly when we look at our common source configuration here in a little bit. The R Thevenin, as I said, is the equivalent resistance of our bias resistors. Most commonly, we're going to be looking at a voltage divider biasing network. So that's just going to be like our R1 parallel R2 that we saw when we were looking at BJTs. And the reason that we did not have a defined current gain in these two configurations is because our input is defined at our gate terminal. And so remember that ideally our gate current is 0. So if we don't have any current, how can we be amplifying it? So it doesn't really make sense to define a current gain. So now that we've seen sort of this overview of our three basic configurations, in the following videos, we're going to be taking a look at each one of these configurations in turn.